Welcome back to Honors Calculus. In this video, we're looking at the chain rule. The chain rule is going to be a tool that will allow us to take derivatives of compositions of functions. So without further ado, let me get my head out of the way and let's dive right into what I mean by that. Right, to start the chain rule, we're going to need a couple of differentiable functions, f and g. Sometimes you'll see this referred to using functions u and v instead, but I think f and g are a little bit easier to work with. I claim that if I want to take the derivative of the composition f composed with g evaluated at x, it's going to be f prime of g of x multiplied by g prime of x. I'm going to go through and prove this and show you that this must work this way, but this is another one of those rules. Sure, you can have it written down, but I strongly encourage you to take this rule and memorize it. The chain rule and the power rule of differentiation are incredibly valuable, incredibly powerful tools that you need to have in top of mind knowledge to be successful in calculus. You will use them so much that if you have to look them up every time, you're going to be lost. All right. But to prove this, I'm going to start off with my definitions of f prime and g prime. I know that these are two differentiable functions, so I know that these two limits must exist. And so if I want to take the derivative of f of g of x, I use the same rule. The limit as delta x goes to 0 of f of g of x plus delta x minus f of g of x all over delta x. And to work with this, I'm going to use mathematicians' favorite trick. Take something where there is nothing and introduce complexity. In this case, I'm going to introduce that complexity. By multiplying and dividing by g of x plus delta x minus g of x, which is defined, right? Right here, we are talking about it. We know we can work with it. And We know that multiplying and dividing by the same thing is multiplying by 1, which doesn't change anything at all. Now I can take those two fractions, I can swap their denominators, right? Commutative property of multiplication, this is still working the same way. And you start to see why this swap was so important, why this introducing this thing was so useful. Because that bit right there, that's g prime of x. On the other side of things, we get things that are a little bit more complicated. I'm trying to write faster than I'm thinking. But we started off our discussion of derivatives thinking about tangent lines and using tangent lines as an approximation. G of x plus delta x, if delta x is small enough, is the same thing as g of x plus delta x times g prime of x. All right, that's the tangent line approximation of g near the point x. And the reason that we want to think about it this way is that this bit right here, delta x times g prime of delta x, that's basically something we can call delta g. All right, so g of x plus delta x is g of x plus a little bit more. And the smaller delta x gets, the smaller the delta g gets, and it will happen in proportion, the proportion being the derivative g prime. So I can think of this as the limit as delta g goes to 0 of f of g plus delta g minus f of g all over g plus delta g minus g, which is just delta g. And then we still have the limit delta x goes to 0 of the second factor g of x plus delta x minus g of x all over delta x. That second thing we said very nicely was just g prime of x. This first thing, it looks weird, but we can find a way to make that look like f prime of g, and g is of course still a function of x. And now that we have the chain rule at our disposal, we can look at a number of functions who we couldn't have studied previously. We've been looking at square roots. What if there was stuff inside the square root? Instead of just the derivative of the square root of x, we want the derivative of the square root of 9 minus x squared. If I think of 9 minus x squared as a composition, f of x is the square root of x and g of x is 9 minus x squared, then I know that I'm going to take the derivative of the square root of x, which we've done in a previous video you can look back on. I'm just going to write down the result so I can save myself a little bit of time. I don't expect you to know that offhand, but that's exactly a problem that we've already solved. And then the derivative of 9 minus x squared is going to be minus 2x, right? The derivative of a constant is 0. The derivative of x squared is 2x. We have a minus in there, so we're good to go. And using the chain rule, I need f prime of g of x times g prime of x. So that's 1 over 2 root x, but evaluated at g of x, that's 1 over 2 times the square root of 9 minus x squared, multiplied by g prime of x, which is minus 2x. Cancel out the 2's, bring everything together. Opposite of x over the square root of 9 minus x squared. I've got plenty of space over here. Let's look at one more example. Sine of x squared minus x. And we want to take the derivative of this thing. All right. We once again have a composition. We have sine evaluated at a polynomial function. So we want to take the derivative of sine, which is cosine, evaluate it at the same point, and then multiply this thing by the derivative. The derivative of x squared minus x is 2x minus 1, just using the power rule. And kind of weird to write it in this order, so we'll generally put the polynomial first. And the derivative of sine of x squared minus x is 2x minus 1 times the cosine of x squared minus x. Right? Now that we know the chain rule, it's doing all the heavy lifting for us. It's just a matter of going through and doing the evaluation. All right, so here's one for you to take a look at. The derivative of 1 over the cosine of x. You might remember from trigonometry, hopefully you remember, that 1 over the cosine of x is in fact the secant of x. So I'm asking you to find the differentiation rule for another trig function that we haven't talked about so far. But take a few minutes, see what you can do with that one, and I'll see you in the next video.